Hey kids, it's Matt here. More thermodynamics. We're getting to the end of it now. We're getting to thermostoich. I've got two more topics for you. This one is going to be about thermostoichiometry, just like we did with just like we did with stoichiometry. Way back in January, we kept track of amounts of substances in chemical reactions. Well, now we're not keeping track of grams or amounts. We're keeping track of joules, amounts of energy. And energy is very important. A lot of chemical reactions we run solely because we want to keep track of that amount of energy. Now, to do this, I've got a couple of examples, but I just want to go back to the underlying premise of exothermic and endothermic. Remember, these terms are always listed in respect to the system. So in an exothermic, heat is leaving the system. So the system is getting cooler. It's going to feel warm to the touch. Now, these are kind of important to us because all combustion is going to be exothermic. Why is that? Why all combustion? Well, it takes a little bit of energy to get a combustion going, but then the idea is it gives off a whole lot of energy as it's happening. Endothermic, these are usually going to be synthesis. After all, why does bonding occur? Why do things combine together and synthesize? To achieve a lower possible energy. That's why bonding happens. Bonding happens to achieve the lowest possible energy. So in this case, are endotherms and exotherms. Okay, exo being out, endo being in. Okay, and we can write or account for this energy in two different ways. First off, we have a methane reaction. Methane gas, CH4, we're going to combine that with a little bit of oxygen, make CO2 and H2O, classic combustion reaction. That's going to release 890. Now we can write this as delta H equals a negative 890, or we can write that 890 as a product. After all, energy is being given off. It's being produced. Comparatively, look at our synthesis problem here. We take carbon and sulfur and we combine those two together. That makes our carbon disulfide. We used that a couple of videos ago when we were doing colligative properties. That H is endothermic. We have to put, we're going to have to put 89 kilojoules of energy into this reaction to make it happen. Put energy in to move things together. Now, just like we did, we can either say H is a positive 89, or we could now write that energy. If it's positive, we're going to write it over on the reactant side. So what's the takeaway? The takeaway is quite simple, my friends. Positive delta H is a reactant, and a negative delta H is a product. That's the takeaway here. Now let's look at our example, because it's really quite simple once we understand the concept of the sign, whether it's positive or negative. The number is very easy to calculate. So it says how much energy is needed when 1.27 moles of sulfur reacts with excess carbon. So we don't have a limiting reagent problem here. Instead, what we're going to do is take our 1.27 moles of sulfur, and for every 2 moles of sulfur, we need to add 89 kilojoules. So we could say a positive here if we wanted. 127 times 89 divided by 2. It's going to cost us a positive 56 kilojoules of energy to convert all 1.27 moles of sulfur into carbon disulfide. So that's the energy we take to put in. Let's look at our other example where we want to generate a certain amount of energy and we want to know what quantity of material are we going to need. So now in this one, how many grams of water, grams is what we're looking for. We're just going to highlight that real quick. How many grams of water would be needed if this reaction yielded 347 kilojoules of energy? It yielded, it produced, it's exothermic. That's going to be a product, all right? Yields, produce, product, exothermic. Either way, take that 347.1 kilojoules, then it's 2 moles of H2O, use your coefficients, per 890, and then turn that into grams. 18 grams of H2O. If this was going to be for CO, we would say 1 mole of CO2 per 890.4 kilojoules of energy. We can make this ratio anything. Just use your coefficients the same way you did with all stoichiometry reactions. These are called thermostoich, and all you're doing is using the chemical reaction now to account for energy instead of using the reaction to account for mass. Very straightforward, getting to the end of thermochemistry here with thermostoichiometry. I'll see you in our next video on Hess's Law.